So if I work this out, what I get is that the first one gives me a plus b is equal to c, and the second one gives me I of k1, a minus b is equals to I of k2, c. So of course, from normalization, we know that one of these constants will be arbitrary and will be set by normalization. So we can choose that constant to be a, then we can express the other constant in terms of that constant. And if you do this, just a bit of algebra, b is going to be equal to k1 minus k2 divided by k1 plus k2 of a. And if you want to be more pedantic, it can be, or not pedantic, but more explicit. This will be e minus v naught square root divided by the factor of m, 2m, and h bar cancel out from the numerator and the denominator. Okay, so sorry, there's a factor of a here. So that's going to be b, and c is going to be 2k1 divided by k1 plus k2 times a, and that's 2 square root of e divided by square root of e plus square root of e minus v naught. As you can see, I like to be very inconsistent in my notation. Okay. Any questions so far?
Sir, I'm still kind of confused with how we mentioned like a plus b equals to c. Like,
oh yeah, sure. So basically, we have a. So what we've done here is that we have. So we have, this is our potential. This is our x, and our potential is a step potential, right? So this is v naught, and this is region 1, and this is region 2. And what we're doing is that we're solving the time-independent Schrodinger equation, because that's the Schrodinger equation, which is the energy eigenvalue equation. So what is that Schrodinger equation? That Schrodinger equation is d squared of psi of dx squared is equal to so here we have h squared, and here we have 2m, and e minus v of psi, right? Did I get the signs right?
Yeah.
Okay, all right. So this is the equation we want to solve. Now, in region 1, v is 0, right? So in region 1, v is 0. So we have d squared psi dx squared is 2m by h bar squared, which I call k1 squared. I think there's a minus sign here, right? Let's just work this out. H squared by 2m, d squared psi by dx squared. So this is the kinetic energy, and the potential energy is equals to E of psi. So if I take this guy on this side, I get an E minus V, and then I get a minus sign. Yeah, so there's a minus sign here. Okay. So this is the equation in region 1, where K1 is 2me by h squared square root. Okay, do you agree?
Yeah.
Yeah. So when this is a positive number, with this minus sign, you can show that the most general solution to this is ae to the power plus ik1x plus b e to the power minus I k1x, okay? If you just plug this in, you'll see that that's the case. Okay, and A and B are integration constants. So, and what is now the equation in region 2? The equation in the region 2 is exactly similar. And it's exactly the same equation, but the value of K is different. So it's K2 squared. And K2 is still a positive constant, but it's 2m E minus V naught by H squared square root, okay? So it's exactly the same equation, but the value of K is different. It's less. So in region 2, so let's call it psi 1. This is psi 2. In region 2, there'll be different coefficients, right? There should be D. D. Okay, is that clear?
Yes, sir.
Yeah. Now, the thing is that, so these are static solutions, right? Now, if I want to evolve it in time, I have to multiply this energy eigenstate with e to the power minus I by h bar e of t, right? This is the time evolution operator for energy eigenstates. If I multiply this, we see that this guy is, because of the relative signs here, because the sign in front of x is the same as the sign in front of t, that this will represent a wave moving in the left direction. And we see that over here, we don't expect a wave moving in the left direction, because what we are expecting on physical ground is a wave coming from here, and some of it getting transmitted, some of it getting reflected. But we don't expect this, right? And because of this, what we are going to do is that we are going to say that, well, then we can just set this to 0, d equals to 0. Then our wave function in region 1 is given by this, and the wave function in region 2 is given by this. Okay, but the thing is that this is one wave equation, and we impose certain continuity conditions. We are working with a potential which has a discontinuity at x equals to 0. So that means that the right-hand side of this equation has a discontinuity. If the right-hand side of this equation has a finite discontinuity, so must the left-hand side. But a finite discontinuity means that the first derivative is continuous. And if the first derivative is continuous, so the first derivative is what you get by integrating it once. So if the first derivative is continuous, integrating it again will give you another continuous function. So what we can say is that, because we are dealing with a potential, because we are dealing with a potential, with a finite discontinuity, the first derivative, psi prime, and psi will be continuous across that discontinuity in V. So that, where is the discontinuity? The discontinuity is at x equals to 0, right? So that means that if I take this guy at x equals to 0, psi of 1 must be equal to psi of 2. And if I look at it, what is psi of 1 and psi of 2? I see that putting x0 here, x0 here, those factors just become 1. Putting x0 here, that just becomes 1. So this gives me a plus b is equal to c. And then similarly, psi prime, the first derivative of psi, at x equals to 0 must be equal to the first derivative of psi at x equals to 0. If I look at the first derivative of psi prime of 1 is I k1a e to the power I k1x plus, so this is a minus I k1 b e to the power minus I k1x. Similarly for psi 2. And if I do those, that gives me that I of k1 is a minus b is equal to I k2c. Okay, is that clearer?
Yes, sir. Thank you.
Okay. All right, cool. All right, so we have solved A, B, and C in terms of A, and then we can write down our energy eigenstate, which will now have both psi 1 and psi 2, right? But, psi 1, I'm putting it in brackets, that'll be at part in the left part of my potential. So I denote that by multiplying by a theta minus x. And on the right-hand side of the potential, it'll be psi 2 of x. And I multiply by theta of x. So what is theta of x? Theta of x is defined to be 1 if x is greater than 0, 0 if x is less than 0. It's one of those distributions. And this is known as the Heaviside step function. Okay. So what does this look like? This looks like if I plot theta of x as a function of x, then it's 0 on when x is less than 0, and it's equal to 1 when x is greater than 0. Similarly, the negative of the Heaviside wave function, Heaviside function. So this is going to be theta of minus x. Okay. Sorry, that's not right. This will be theta of minus x. Okay. So does it make sense why we are writing this multiplying? So this is just saying that this wave function on the left side of the potential looks like this, on the right of the potential looks like this. Okay. Okay, so let's explicitly write this. So explicitly, what we have is, so one thing we can do is that we know that E is equal to, 2me by h bar squared square root is equal to k1. So we can replace E by k1. And so psi of E can be replaced by psi of k1 because we can always use this formula to go from one to the other. And then we have psi of k1, which is a function of x. So this is the energy eigenstate. Is A, I'm factoring out the A. And inside I get e to the power I k1x plus b over a e to the power minus I k1x multiplied by theta of minus x plus c by a and e to the power plus I. Now instead of k2, I'm writing it in terms of k1. So what is k1? K1 can be expressed, E can be expressed in terms of k1. That's what we're doing. So we get k1 squared minus 2m v naught. And this thing has over h bar squared square root x theta of x. Okay, so this is my energy eigenstate. Okay, any questions? So yeah, so this was our step one. So we have achieved step one. We have figured out the energy eigenstate of the Hamiltonian of A with a step potential. Taking into consideration the fact that we are expecting, we are looking for a specific type of energy eigenstate. We don't have the D. We set the D equals to 0 because we are taking into account the boundary condition that our initial particles will be incident on the potential from the left.